So, last time we saw what the graphs of sine and cosine look like. Sine we did by plotting some points and then thinking about periodicity and the symmetries that sine has. We thought about cosine by saying, well, cosine is just a shift of sine. So take sine, shift it left by pi over 2, you get cosine. So that's easy enough. From this graph, can you now answer a bunch of reasonably easy questions? What's the max value cosine achieves? Still 1, right, because it's a shift of sine. It's got to be 1. By looking at this graph, can you read off the inputs that achieve it? And let's start by just listing them, I guess. It looks like there's an input that achieves an output of 1. What input is that? 0. What's the next input where you see it happen? Pi? In fact, do you think basically all of the places that maximize satisfy that same pattern? They're just some multiple of 2 pi. For some whole number k. How about minimum? What's the least value that cosine achieves? -1. Again, it should be the same as sine. I guess you can also see it from the unit circle, right? The trig functions, the cosine in particular is the x value of a point on the unit circle. What's the most negative x value you see on the unit circle? Well, it's 1. It's -1. So there's the minimum value. What are the inputs that achieve that minimum value? And let's just start listing them. What's one input that does it? Right here, a -pi. That does it. What's another input that does it? Another one? 3 pi? Is there some sort of pattern that you see there? It looks like any odd number multiplied by pi should do it. Any odd number times pi. And maybe if you want something that looks more like a formula and less waddy, x equal to, let's see, what is an odd number? It's an even number plus 1. So there's another way of saying any odd multiple of pi. It's an even multiple of pi plus another pi. And I guess I don't need those parentheses now. Groovy. Does that feel pretty good? Even or odd? I hear an even? And in fact, we already knew that. We already knew cosine of -x is the same as cosine of x. Can we play the same increasing, decreasing game that we did last time? I think so. Let's start at 0 and tell me something about increasing or decreasing this starting at 0 or ending at 0, having to do with 0. Yeah. From -pi to 0, it is increasing. Well, -pi to 0, I'm not going to divide by 0. -pi to 0, it is increasing. Okay, cool. What's something else you can tell me about monotonicity? Either increasing this or decreasing this. Yeah.
No, but how I don't figure out.
Cool. So from looking at a graph, a function is even if when you reflect it over the y-axis, you get the same thing back. So let's see if that is true. So there's the y-axis. Do I see the exact same behavior on either side of the y-axis? Yeah. it is also true because cosine of negative x is the same as cosine of x, which is one of the things we got by actually drawing some pictures. Nice. So from negative pi to 0, it is increasing. I guess that means at 0, it starts decreasing. So it's decreasing from 0 until, let's say it loud on, pi. So at pi, I guess it starts increasing again. What's the next interval of increase? Pi to 2 pi it is increasing. And maybe there's some sort of pattern that's emerging. So starting at 2 pi, how long does it keep decreasing? 2 pi to 3 pi. And I haven't drawn any of those here, so let's just check that. There's 2 pi to 3 pi. Yeah, it's going down. In fact, I think those two each are enough to notice some sort of pattern. It looks like you have a bunch of intervals, each of length pi. The increasing ones seem to start at odd multiples of pi and end at even. The decreasing ones seem to start at even multiples of pi and end at odd multiples of pi. So where are all of the turning points? Let's list some turning points. Where are some turning points? Pi is a turning point? Let's list it up to notice a pattern. Give me more turning points. 2 pi. Another turning point. 3 pi. So it looks like multiples of pi. Does the same pattern also go the opposite direction? Yeah, so maybe I'll write 0 and negative pi just to make it clear I want to include negatives and include more ellipses. People feel pretty good. So you can read off lots of things by just looking at the graph of the trig functions. Turning points, intervals of increase, decrease. Is it even? Is it odd? Where is it maximized? All the normal stuff. Let's start doing some other things with these. Let's start thinking about something that won't seem terribly surprising. If you know how to graph cosine of x, then of course you know how to graph things like 2 times the cosine of 3 times x. And I think we'll go up here and do this in a moment. Here I want to finish this sentence first. So you would start with the graph of cosine, right? Now you should think of cosine as like an elementary function whose graph you should just know. What happens when you take the x inside of the function and multiply it by 3? What does that do to the graph? Yeah, so it either makes it wider or smaller. And the way to remember is it's inside the parentheses. You're doing it to x. So it always does the opposite of what seems most obvious. So it'll compress. And then if you think about it for a moment, it makes sense. The x multiplied by 3 means that anything that happens horizontally happens in one thought at a time. It happens 3 times as often. So what will this 3 achieve? X values get divided by 3. What does multiplying a function by 2 do to the graph of that function? Yeah. Perfect. Yeah. So the y value is the output. That'll take cosine and multiply all the outputs by 2. So all the y values get doubled. Y values get multiplied by 2. So it looks like we would start with the graph of cosine and do those 2 things to it. And maybe the right place to begin is, what does the graph of cosine look like? And I'll tell you this for free. One of those 2 is cosine. Maybe I'll color code so it's easy to answer which one's which. So here's blue one. Here's another one highlighted in orange. Which of those two is cosine? I hear a call for orange. Convince me. Why orange? Did I? You said blue. You said blue. Okay, then convince me. Tell me, why blue? Starts at 0. Yeah, so let's think about that. I see this point 0, 0. So let's remember that really quickly. What's the cosine of 0? It's 1, isn't it? Wait, so could the blue one possibly be cosine? No. And in fact, maybe here's another way. There's the graph of cosine. Which one does that one look like? I think it's the orange one, right? So the orange one is cosine, and that's an easy thing to get wrong. They're such similar functions. They are just shifts of each other. So try to think about the things that you know about cosine. Like, what is cosine of 0? Is cosine... Oh, so how about this? Is cosine even or odd? Even. Which of those two is even? Orange. So I think blue isn't cosine. Orange is cosine. Nice. Cool. So now let's go through these motions. Let's do these two things to it. Does it matter what order you do those two things? No, so I think we can just do them both at once. Right, if you were also doing shifts, then you would want to worry, but as is, we don't have to. So, doing that, let's label some points here. So, I see this point at 0, 1. Where does that point go when you do those two manipulations to it? It goes up to 0, 2. All the y values get multiplied by 2. And let's also just let's trace those 5 points out. So here's the point that has a y value of 0. What's that x value? The y value is 0. I hear a pi over 2. And maybe here's unit circle way to see that. That point has cosine equal to 0. Cosine is the x-coordinate on the unit circle. So here we see pi over 2 comma 0. What happens to that point when you do these two things to it? Well, the x value gets divided by 3. So the x value will be pi over 2 over 3. What's pi over 2 over 3? If I divide something by 2 and then divide it by 3, that's the same as dividing by 6. Yeah. So I see this point right here at pi over 6 comma 0. That point down here is the point pi comma negative 1. So where will that point go when I do this stuff to it? The x value gets divided by 2, so pi over 2. Pi over 2. And what happens to the y value? Wait, why pi over 2? X values get divided by 3. X value becomes pi over 3 because the x values get divided by 3. Y values get multiplied by 2, so what's the y value? -2. Cool. So that gets us this much of the graph. And I think from there we have a pretty good idea what should happen from here on. Let's trace at least these two remaining points. So this point was 3 pi over 2 comma 0. So where does that point, 3 pi over 2 comma 0, go when you do these two things to it? I hear a pi over 2 comma 0. Anyone disagree? Yeah, right. You divide by 3, the 3 in the numerator cancels. And stretching vertically doesn't matter if you start at 0. And then finally this point at 2 pi, we'll wind up at 2 pi over 3 comma 2, I guess. So now that we have this much of the graph, how do you think the rest of the graph should look? Yeah, just say it louder. I think that was your yeah. The graph up here went from 0 to 2 pi and then it repeated. Same thing here. I'll see that chunk of the graph and then it will repeat. So maybe I'll box this off. And then I'll see the exact same pattern over again. Up to 4 pi over 3 comma 2. And the same thing will happen in reverse. Negative 2 pi over 3 comma 2. And so on. That feel pretty okay? So let's try to read off some things from this. So I'm going to jump down to the bottom-ish of the page. So the period of a function is how long until it repeats. That is, like, how far to the left do you have to shift it? Or to the right do you have to shift it before you see the exact same thing again? So what's the period of that function? How far to the right would you have to shift it to get the exact same graph? 2 pi over 3. So if you like, this length is the period. Period equals 2 pi over 3. So I think I'd like you now to do one quite similar. I think just for the sake of variety, maybe I'll replace that cosine with a sine. Sketch for me, if you will, the graph of 3 times the sine of x multiplied by 2. So replace that cosine with a sine. And then answer that same question. What is its period? You all are allowed to talk to each other through this if you want to. Cool. So maybe I'll start by just asking this. So I guess the elementary functions to start with are the two at the top of the page. Which one should you start with in order to graph this one? The blue one, because the blue one is sine. So the graph will look, and maybe I'll even sketch one period walk. Should look something like that. Let's label some points. So I guess this point is free of charge. It's 0, 0. This point where that max occurs, what are the coordinates of this point? Here are pi over 4, comma 3. People agree? Yeah. And so it should be like this point, but the x value gets divided by 2, and it used to be pi over 2. Y value used to be 1. Now the y value is 3. This x-intercept, where is it? I hear a pi over 2, and I guess I already said x-intercept, so comma 0. This minimum, where does it occur? 3 pi over, just say that again, 3 pi over 4. Okay, cool. By what y value? Negative 3. Awesome. And I guess that next point will be just pi, comma 0. Neato. People agree with that much? And then, well, I guess the rest of the graph should look basically the exact same, just copied over. Good enough. All right, so let's answer this question. What's the period of this function? Pi. So I guess here's the starting point. These two things both have period 2 pi. When we took the x and multiplied it by 3, we had period 2 pi over 3. When we took the x and multiplied it by 2, we wound up with a period of just pi. There's a general formula here. If you write down any stretched and shifted trig function, you can compute the period free of charge using the following rule. Flipping to the next page. The period of cosine of a number times x, or sine of a number times x, is, let's think about it for a second. That's going to take the x's and multiply by some number omega. What does multiplying the x's in a formula by a number do to the graph? Compresses it by a factor of omega. So previously the period was 2 pi. What do you think the period will be after you do that compression? 2 pi divided by w. It's supposed to be the Greek symbol omega, but it looks a lot like a w. That's forgivable. 2 pi divided by omega. And there's one subtlety here which hasn't appeared in any of the examples so far. What if that number omega happens to be like negative? Do you think it makes sense for the period to be negative? You could make sense of what it means for the period to be negative. You could, like, well, instead of shifting right, you're thinking about shifting up, but you go left and right anyway, so who cares? But maybe I'll throw out the negatives by taking an absolute value. That seem pretty okay? And maybe let's just do one quick sanity check. Let's sketch a graph of sine of pi times x and use this rule. So, let's see, if you wanted to sketch the graph of sine of pi times x, there's going to be some back and forth flipping. Sine goes through 0, 0. The x coordinates are all going to get divided by pi, so that x value is still 0. So it still goes through the point 0, 0. And I'll just track a few points. So there's this point here at pi over 2, comma 1. What's pi over 2 divided by pi? Just 1 over 2, the pi's cancel. Pi over 2 over pi is just 1 over 2, so this is the point 1/2, comma 0, and in some sense that's enough. That tells you it should get back down to 0 at 1, 0. This minimum should happen at 3/2, comma -1, and then it should come back up to 0 at 2. And then it will repeat. Why would it be 1/2? It wouldn't be 0, would it? Does that look like a y value of 0? What y value should that be? 1. Yeah, I mean, when it's clear I've done something that's just obviously wrong because it makes no sense, you can assume that I did it wrong. You can just tell me I did it wrong. I guess it's often more diplomatic to ask, why is this that, instead of, cool. So, by looking at this graph, what's the period of this function? 2. According to this formula, though, it's apparently the period, well, I say although, I'm just checking if the formula is correct. That should be 2 pi divided by the absolute value of pi. Does that simplify down to 2? Yeah, the absolute value of pi is still pi. 2 pi over pi is 2. Checks out. Nice. That feel pretty good? Groovy. So, there's one last concept that will be discussed in the homework regarding this that I don't want to say much about in class. This is like one of the, no, I'm actually going to make you read the textbook prompts. There's a concept called amplitude that you can also compute. If you like, the amplitude is how far above the average value does the function get. So those values are both equal to the amplitude. So what does it look like the amplitude of this is? Think about that while you're doing some of the homework problems. It'll ask you to compute some amplitudes. And maybe just for the sake of seeing one more, let's compute the amplitudes of these. So this looks like its average value is still 0. What would you say that amplitude is? I heard a 2. I heard a pi over 4. Do I hear any others? I hear a 3. Let's hear just a call for unity. 2. Pi over 4. 3. Cool. Let's compute. So this distance is the amplitude, the distance down to the x-axis. But the distance down to the x-axis, that's the same as the y-coordinate, right? What's the y-coordinate of this point? 3. So that's why the amplitude is 3. Cool. People find that useful? Nice. So we've graphed sine, we've graphed cosine, and we've done some stuff with the graphs. I've talked about what happens when you stretch them. There are like 4 other trig functions, though, aren't there? But if you know sine and you know cosine, how hard could it be to figure out the rest? So we'll figure out the rest straight away by using the fact that, well, they're basically just sine and cosine with some algebra done to them. Let's start with tangent. And just like sine and cosine, like I thought about the graph over one period, and then I shifted. Let's graph tangent over one period, but let's remember what the period is first. And to do that, let's just remember what the tangent of pi over x is. Tangent of pi plus x is. And, well, how would you figure that out? That seems like a reasonable start. Yeah, because I know what sine and cosine do when you add pi. Sine of pi plus x over cosine of pi plus x. And that's useful because what's the sine of pi plus x? I hear a negative sign, but that had a question mark at the end, it sounded like. So this is why, like, on the cover page of the previous set of notes, there's like the table. Just to make it easier to reference. Of course, since I attached this all together, how useful is it really? All right. So by flipping back to this, what's the sine of pi plus x? Negative sign of that same input. This says theta. It doesn't matter what you call your variable. What about the cosine of pi plus x? Negative cosine. So let's do that. This will now be negative sine x divided by negative cosine x. Oh, neato. What's that equal to? Just tangent again. The negatives will cancel. So it looks like when you add pi to the input of tangent, you get tangent back. So what's the period of tangent? Pi. Tangent has half the period of sine and cosine. So that means if I can graph tangent over an interval of length pi, so from 0 to pi, for example, it could also be negative pi over 2 to pi over 2, or any other period of length pi, we'll know everything. So let's try to do that. And let's start by saying, well, tangent is sine over cosine. So let's start with just what are sine and cosine from 0 to pi. And well, we already know. It's on the previous page. Sine is the y value. It starts at 0, goes up to 1, and back down to 0. And then I'm at pi, so that's as far as I care. And I think this is the opposite color coding from the previous page. That's okay. So there's the graph of sine x over this interval. Here's the graph of cosine of x. So let's start with this. Where is tangent positive and where is it negative over this interval? And let's start from 0 to pi over 2. Is cosine positive or negative? How about sine? Also positive? So what can you tell me about tangent? Positive. So tangent from 0 to pi over 2 is positive. Sine from 0 to pi over 2 is positive. So tangent, because that'll be sine divided by cosine. Positive divided by positive is positive. How about from pi over 2 to pi? Yeah, where in this case by you mean tangent. Because it will be sine is positive divided by cosine is negative. Positive divided by negative is negative. All right, so let's think about that. The graph is going to wind up being down here. it'll go from positive before pi over 2 to negative after pi over 2. So I'll try to draw this graph so it's positive and negative in the correct places, so it has the correct vertical asymptotes, and so it has the right x-intercept. So let's try to find that. Let's try to find the x-intercept. So tangent is a fraction, sine over cosine. This will be 0 when the numerator is 0. Between 0 and pi, when is sine equal to 0? I hear a pi. Is that the only number? Yeah. Right. Sine is 0 there. Sine is 0 there. So I'll draw in those two x-intercepts. There is a vertical asymptote when you divide by 0, just like we saw for rational functions. So where is this thing's vertical asymptote? Pi over 2? Is that enough information to get some sort of graph going? So I need to go from this x-intercept to that vertical asymptote. It has to be positive. So I guess it better do that. Next, it needs to go from this x-intercept to that vertical asymptote, but it has to be negative. That look like a reasonably good picture? So I'll copy that down here from 0 to pi. And how can you get all of the graph now? Just to repeat, this thing is pi periodic for the top of the page. So if we graph it from 0 to pi, we can now graph it everywhere by doing the exact same thing again. Cool. That seemed pretty all right. All right, so there's the graph of tangent. Do you think we could probably get the graph of cotangent doing basically the exact same stuff? So we'll do the same walk, but faster for cotangent. Maybe I'll start there. So cotangent is just the reciprocal of tangent, right? Cotangent is the same as 1 over tangent, except for the issues about dividing by 0. Right. You need to decide that 1 over 0 should be 0 if you want this to be true. But no. Anyway, I'm belaboring a point that doesn't matter right now. So cotangent, let's see, that is cosine over sine. So let's use the exact same reasoning. Let's think about the graph of cosine and the graph of sine. So there's the graph of cosine. There's the graph of sine. Oh, neat. So comparing cotangent to tangent, where will it be positive, where will it be negative? Exact same places. Right, instead of having a negative divided by a positive, you'll have a positive divided by a negative. That's still negative. So positive and negative in the exact same places. Let's try to get intercepts and asymptotes. So tell me, so this thing has a 0 when the numerator is 0. By looking at that graph, where is the numerator? By that, I mean this graph. Where is the numerator of this thing 0? I hear pi over 2. Because of this point. There will be a vertical asymptote when the denominator is 0. When is the denominator 0? Well, the denominator is sine, right? This one is sine. Tell me, where is that 0? Yeah. 0 and pi. Yeah. So there will be a vertical asymptote at 0, vertical asymptote at pi. Oh, nice. Does that mean you can now sketch the graph? I think that looks reasonable. And, I don't know, I guess we could even think of it this way. Maybe this is a better thing to have done for tangent. Tangent is the slope of the line. So there's a line of slope 0. As the angle goes up, the slope becomes bigger and bigger. So it increases until it makes it to the vertical asymptote. Oh, and then the slope is really big and really negative. And it becomes less negative, less negative, less negative until it gets to 0. So I think that agrees with the previous page. All right, so let's copy this down. So there's the graph of cotangent from 0 to pi. So how do you get the rest of the graph? Repeat. Yeah. Nice. Feel pretty good about that? So, yeah, that's okay. So we have the graph of tangent, we have the graph of cotangent. I think we have enough time to get the graph of at least one of secant and cosecant. So let's do at least one of those two. Which one should we do, secant or cosecant? It'll be super similar walk either way, right? Because they're really similar functions. Secant? Cosecant? I think the secants have it. I guess it being the next one in the list is not a bad reason to do. So, secant is 1 over cosine. Cosine has period 2 pi. This should also have period 2 pi, so we can't play the game where instead we restrict ourselves to just 0 pi. We have to go all the way from 0 to 2 pi. So, secant is just built out of cosine. So let's start with the graph of cosine. So tell me, where will secant be positive / negative? Did I screw up? Is that the graph of cosine?
Period 2 pi. Oh, yeah. There we go.
Well, happy? Yeah, right, I mean, like, from 0 to pi, it looks really similar to negative pi. Yeah. Okay, awesome. So, let's figure out positive / negative. From 0 to pi over 2, is cosine positive or negative? So will secant be positive or negative? In fact, right, from 0 to pi over 2, all the trig functions are positive. It's quadrant 1. How about from, well, I guess if it's positive there, maybe it changes. Tell me where cosine / secant will be negative. All the way from pi over 2 to 3 pi over 2. It is negative over this range. So I guess it'll be positive the rest of the time. Is that correct? Nice. All right. Now let's do the intercepts and asymptotes thing. Secant is equal to 1 over cosine. It is 0 when the numerator is 0. When is the numerator of that fraction 0? It's not, it's 1. Oh, wait, wrong place. This fraction has a vertical asymptote when the denominator is 0. Looking at this picture, where is the denominator 0? Pi over 2 and 3 pi over 2. All right, so I'll put those on the graph. Pi over 2, there's a vertical asymptote. 3 pi over 2, there's a vertical asymptote. And I don't have any given values because there were no x-intercepts to work with this time. So instead I'll think about extreme values. I'll think about what's the smallest this could be by thinking about what's the biggest that cosine could be. What's the biggest that cosine of R is? What's the maximum value of cosine? 1. So if cosine maxes out at 1, secant should like minimize out at 1, up to some issue with positive or negative signs. So let's just think about when is secant equal to 1 over cosine equal to 1? And when is it? When cosine equals 1. Very good. And when is cosine equal to 1?
0, 2 pi.
All right, that gives me 2 points. I have this point here at 0, 1. I have this point here at 2 pi, comma 1. And those will be like extreme values. Those are those who will at the very least be local minima. So we'll open upwards from here to get to these vertical asymptotes. That seem pretty okay? When is secant equal to negative 1? Yeah. When cosine is equal to negative 1. Excellent. All right, the only way 1 over a number could be negative 1 is if you divide it by negative 1. And now take a look at, well, I guess either this graph or the unit circle on the board. When is cosine equal to negative 1? Yeah, but say it louder. At pi. So, at x equal to pi, I will have an output of negative 1. Cool. So there's the graph of secant from 0 to 2 pi. How could you now get the graph of secant for the rest of time? Same as the other ones. So, there's the graph of secant. Do you think you would do something pretty similar to get the graph of cosecant? Yeah, I think you could follow like all of the exact same laws, but replace cosine with sine, and some things would change. Well, you could notice sine is just a shifted copy of cosine, so cosecant should be a shifted copy of cosecant. Nope. Cosecant should be a shifted copy of secant. Groovy. So, now you know all the stuff you need to know about graphs of the trig functions. And, in fact, even if there's something that you don't remember about the graph of a trig function, here's how you can reinvent it on the spot. Just think about what it has to do with sine and cosine. Do the appropriate bit of division.